Hello, guys. So the next set of speakers is a team that participated this past SCUDEM 5 in, they participated in modeling a challenge. And here they want to give an entire experience of the viewers seeing what their model was and give a little bit of their experience of how they felt the competition went. And Miles, Chenming, and Henry, they are undergraduate students at Florida Institute of Technology in Melbourne, Florida. So,
I just need to interrupt. I apologize for not introducing Anthony. Anthony Stefan is a graduate student who's been very helpful. Been an intern and has participated in SCUDEM as a student, as a coach, as a host, and has led these three off the cliff. So you're on.
Go ahead, guys.
Can we present? Henry, can you share your screen, please?
Yep, I can do that now. Go here. Can you see my screen?
Yes, we can.
Perfect. All right. Hello, everyone. My name is Henry Bay.
My name is Miles Pophal.
My name is Chenming Zhen.
And we have our SCUDEM 5 competition that we conducted about 2 months ago. And this is a competition of three problems. And we picked one and we spent about 3 weeks designing our model and solving the problem. And we have a 10-minute presentation at the end to show everything off. And this is our presentation here along with some of our reflections and what we have learned in the process. So we chose the physics problem, and we seek in here to explain the problem clearly and concisely and apply the natural assumptions. And we're going to show how the general model follows from the assumptions. And then we're going to reduce the model to an idealized case for sanity checking. And then we're going to demonstrate the model with some simulations. And then we're going to conclude with some initial conditions and some limitations. So our problem is a viral video. It shows a bird perched on a bicycle wheel, and it's able to move itself so the wheel spins. And our job is to model this phenomena with a small apparatus that is attached to the wheel, and it's able to move a mass to generate this motion. So our apparatus would consist of a small piston that is capable of moving the piston radially outward or inward. And this can be imparted with some angular displacement or velocity. So like a nudge, that will give some initial lateral movement. And this comes from the bird leaning to start the motion. And then actually in the later, we'll see that it satisfies the initial conditions for the angular position and angular velocity. So this is an example. This is like a model that we created. So you see the mass retracting when it goes up, but when it's going down, it actually pushes itself up. So it keeps itself spinning back and forth. So now we go into the equations of motion. So from physics, we know that linear velocity is the radius function times theta dot, which is the angular velocity. And angular position is just theta of t. And because in here, you'll see from the free body diagram that we start from the vertical axis, the x-axis, the x-coordinate is going to be sine of theta, and the y-axis is going to be cosine of theta. And in the r theta, is distance from the axis of rotation to the center of mass. So we're going to apply some fundamental assumptions here. So our bicycle wheel and the apparatus represents a rigid body. And our apparatus impacts the motion by moving either closer or away from the bicycle wheel, as you have seen in the diagram. And when we think of the rotational motion, we can think of it as Newton's second law. And in this equation, the taus represent the torques, and I is the moment of inertia. Alpha is theta double dot, which is angular acceleration, and 0 is actually a zero vector since it's a cross product. And we also assume that the time that piston moves between the two states that we have seen has a negligible impact on the motion. So we just say it's instantaneous. So this is like our description of the free body diagram. It starts from the vertical axis, as you see the theta here. The gravitational force is always going downwards. And the friction and the air resistance is always perpendicular to this radial vector.
So following up on that, we want to go through and want to talk about what these torques actually are made of, right? So we know that as we go, gravity's kind of like powering, it's driving our motion. So we're going to have some torque by gravity. And as we saw, air resistance and friction kind of go against our motion. So we're going to have torques by those two. We also have like an assumption, a little assumption here that we're going to say these forces act on close enough points to be treated the same, right? We have a bird on a bicycle wheel. We're not modeling some large jet engine or something like that. We got a nice small system. And so when we go to the torque, which is the distance vector crossed with the force vector, in terms of magnitudes, it's going to reduce down to the magnitude of the force and the magnitude of the distance only because they're tangential. Most part. So you see, now we're going to turn back to that equation of torques and angular acceleration. We're going to say, okay, it's equal to the zero vector. And we know that the zero vector is the only vector uniquely determined by its magnitude. So we're going to reduce it to an equation of magnitudes, since that's going to make our situation a lot easier. We're not dealing with a system of equations. We only have one equation. So we got a sum of magnitude of torques and then the sign term. That just represents if it's with our motion. So like gravity's with our motion when we're coming down, or against our motion. So gravity is against our motion when we're going up. I'm going to go through. So first, you go back a slide. The torque by air resistance is just, we assume proportional to velocity squared for the force. And so once we plug in and convert back to angular velocity, we're going to get it's proportional to the cube of the radius and the square of angular velocity. Similarly, we're going to get that the frictional force, which is proportional to normal force, is going to be proportional to the radius squared and angular velocity squared. Finally, torque by gravity, this one does have a sine theta term because gravity isn't tangential all the time. It depends on where we are on the wheel. And that just comes from force gravity again, so that one's pretty standard. And the moment of inertia term, angular acceleration, that stays the same. We can plug in for the moment of inertia because we have a bicycle wheel. So that's a nice like a closed form expression we can plug in. We can combine all our terms in that earlier equation to get this. You see second order term, right? We got angular acceleration, second order equation, homogeneous, it's equal to 0. Autonomous, we get only in terms of theta, and theta is our dependent variable here. Time is our independent. And of course, nonlinear because you got like the squares of angular velocity. And then finally, to pull it down one more step, every single term has an R term, which is never 0, so we can just factor out of the equation, ignore it. And now we want to define this radius term because we've just built this like an abstract idea. If we were to try and maximize this radius as like in the sense that the bird will get the most energy and will keep going and going and going, that's a variational problem. We can't do anything like that. But what we can do is simplify. We can say, okay, we extend when we're coming down, we contract when we're pulling in. That'll give us the most energy. So we do that with the Heaviside function. We start when sine theta, remember we're measuring from the vertical here. So when we're positive, then we extend, or negative, we contract. Now we can do some further simplifications, just like with that Heaviside function. So the torque and air resistance are going to be really small, right? We've got a bicycle wheel and a bird on it. That's not going to generate a lot of air resistance. It's certainly not a lot of torque. So we can kind of eliminate these terms in the equation. They're going to be very small. But one thing that we should realize is this equation is now going to show our system will increase speed without bound because there's nothing stopping the motion. So it's just going to keep going faster and faster and faster. And that'll lead to the equation on the bottom in terms of the angular acceleration, gravity, sine theta. Now we're going to do some numerics with Chenming.
And here for the numerical simulation, we have selected several pretty reasonable constants. For example, the R1, R2, M, and G. Those are very standard for a bicycle wheel. And K is our air resistance constant, and mu is our frictional constant. One thing to be noticed here is that theta dot 0 equals to 4 radius per second. That's more than 1 revolution per second. It's quite fast for a bird perching on a wheel. We chose this specifically because that shows a better result. And we applied a fourth order Rocky-Kata scheme for the second order ODE because of the incredible variance from the initial condition. And later on, we'll show a longer time frame to see a further analysis review. And here on the left-hand side, we have the angle versus time graph. And on the right-hand side, we have cosine of the angle versus time. And the red line represents the ideal model, and the blue line represents the full model. We can see that the full model is lagging slightly behind the ideal model. Well, that matches exactly what we are imagining about, because with the air resistance and friction, we know that they go against our motion. So our full model should be lagging behind. Next, please. And running the simulation from 0 second to 4 second, we extended the time interval. And on the left-hand side, you can definitely see a huge divergence from the two models. That is because our full model did not make a full revolution and started to swinging at the bottom because, due to the friction and air resistance. And on the right-hand side, you can see that at time equals to 2.5 second, or cosine theta, cosine angle did not reach 1. But one thing to be noticed here is that at time equals to 4, our cosine angle actually increased. That's due to our numerical error because, from the physical understanding, we know that it should be swinging with less and less motion. And as we talked about before, we have shown that our full model is lagging slightly behind the ideal model, and this provides a sanity check since our air resistance and friction go against the motion of the apparatus. And this model is very difficult to predict and is very sensitive to changing initial conditions. And also prediction for longer time range time becomes more inaccurate, meaning the longer time difference from our numerical scheme.
So now what we're going to do is we're going to try and find if we ever reach some maximum velocity and what conditions we give that to us. So first of all, if we're going to look for a maximum, it's going to be on some time interval, right? So start from 0, go to somewhere else. And on a maximum, it's either going to occur on the boundary or on the interior. Now at 0, that started off boundary. We don't really care about that because that's our initial condition. So we define the velocity there. The right side boundary, we don't have an upper bound in our problem. So it can be whatever. We don't know what's going on there either. But on the interior, if we have a maximum, the second derivative must be 0 because we're maximizing the first derivative, and the derivatives exist because we're a second order differential equation. It has to exist. So if we plug in that second derivative equal to 0 and try and solve down our equation for that first derivative, so angular velocity, what we're going to get down is in the bottom an actual expression for the angular velocity in terms of the angle, which we need to convert this angular velocity to linear velocity. So that means we need to factor the distance, which when we plug in, and we can do some simplifications to get that final expression at the bottom. And our velocity in terms of the angle is going to be, it's like mass, gravity, sine theta, got the constants there. We know sine theta is maximized at 1. So when we plug that in and plug our initial conditions in, we get a pretty fast 16.9 or so meters per second, very fast. But some things to take into account is that we kind of assume a maximum exists. If the maximum doesn't exist, then our second derivative equal to 0 doesn't make sense. In the same way, if we don't have air resistance or friction, the denominator is going to be 0. So our velocity is just going to be unbounded, which is what we expect, right? Without the dampening effects, we're going to go to an infinite velocity, what we expect. Now we're going to talk about some initial conditions with Chenming again.
So here we wonder, what if the initial conditions changes? Well, so first case, what if we start at the bottom? And of course, with a high enough initial kick, for example, theta dot 0 equals to 8 radius per second, and here's what motion would look like. It looks really like when we start from the top, which is expected when we have a kick, we'll just start spinning and spinning. Next, please. And with no initial velocity, well, the graph on the left-hand side indicates that we don't have any motion at all. This is also passes a sanity check since no motion, we don't turn. And on the right-hand side, if we do have a slightly position offset, we do still get to start moving, but slowly. Next, please.
So we're going to discuss briefly about some of the limitations that we had in the model. So at our speeds, the air resistance and rotational frictions are nearly meaningless because of the lower values. And our fourth order numerical scheme becomes more unreliable as the time increases, the time interval. And we also rely on knowing the center of gravity for the apparatus. And we also use the Heaviside function for the radius function, but this is only a simplification, in no way a perfect fit for our model. So to summarize the whole thing, we set out to model the motion of the bird on a bicycle wheel. And we found that with a given radius function, we can keep it spinning with increasing speed. But we also found that depending on what initial conditions we have, we may not be even able to complete a single rotation. After that, we found expression for the maximum speed, and we sanity checked our model with some numerical simulations, and then we considered some of the limitations of our models. So talking about the whole SIMIODE experience, I really loved working together with everyone. I think the teamwork aspect was one of my favorite thing about this competition. The fact that you're not working by yourself solving problems, but I mean, you're working as a whole group and you're trying to get this one problem down perfectly in a model. So I really love that aspect.
For me, it was this like the moment when all our work, when we were just sitting down, trying to figure out the model and everything clicked. We found our strategy to approach the problem and all our work paid off. After that, everything else like didn't even feel like work because it was just so quick and it just flowed so nicely compared to the work before. So that epiphany moment was my favorite part.
And for me, the most interesting part for me should be the application in the modern science, because it's nothing like what we have, you know, in the textbook problem, where the problem statement is very clear, all the conditions given. But here we have to make our own assumptions, you know, build our own model, run the simulation, see if there's something wrong, come back to the model, modify it, and then run the simulation again to see if it matches the actual physics. I think that's really impressive. And at the beginning, at the end, a very special thank you to Anthony Stephan for getting us interested, and for SIMIODE and SCUDEM for taking the time to watch, review, and judge our presentation. Thank you.
Thank you. You have any questions? Anyone?
Yeah, any questions of people out there? I was interested in your concern about initial velocity. You said that theta prime of 0 was 4 radians per second. That's what you felt you needed to get it to go around to at least come up one time. Is that it?
It was more so because in our graphs, I don't know if the screen share is still up, but in the graphs on that longer time interval, we could see like a huge divergence. So it took a lot of tinkering with the initial conditions to get that. We could get rotation with a much lower speed, but we would just have to run it over longer, and we wouldn't get that divergence we saw in the long time interval with.
Okay.
Yeah.
This epiphany moment, you said you worked for 3 weeks, right?
Yes. So
how much, when, the epiphany moment doesn't occur right away, right?
Oh, no. It was probably a little over a week into things.
Right.
And we were working on the model. So I think I suggested working with like work energy theorem, and everything was in terms of integrals, and it wasn't working out. We weren't getting anything nice. But then I think Henry suggested just working with torques, and then we could use like this Newton's second law analogy of torques and rotational motion, and it just worked perfectly. Everyone's like, wow, we have formulas for torques here, and we can just go right through it.
In a video for our first SCUDEM challenge that we ran in New York City in 2017, actually in upstate New York, and Boyan was there, our next speaker. One of the groups said, we argued a lot. How did you guys get along together? You obviously have strong opinions about something technical, but you have to defend it, right? So you know, and I also assume you have respect for each other, but how did you get along, I guess?
I think we just had long discussions. Like every time, like we would give someone time to just present the idea, and we would all sit down and listen to like what the idea is. And then after that, another person would present it, and we would kind of like vote it, kind of weigh the alternatives, like what is good, what is not. And then eventually, with enough time, we would reach an agreement, and everything would work out. So that was really great.
Yeah. And also, me and Henry actually participated the SCUDEM in 2019, and then we're working as one team, so we get along pretty well. And Miles, me and Miles working in the school side by side as well, so you know, we kind of know each other, so it feels pretty comfortable working with my teammates.
Okay. And were you remote, or were you able to get together, you know, physically? How did it work?
Oh, that should, we're really thankful for Florida Tech providing us with the space, and also Anthony really helped us on this. We managed to get together and we have a big classroom, shared screen, and a touch screen TV. That was pretty awesome. Yeah.
Wow. So you spent a lot of time watching basketball and other things,
No,
I guess?
no.
No.
We got
okay.
pizza, not sports, but we got pizza though.
You got pizza. Well, there you go. That's the one good thing.
I,
It was like,
I have to run to the session that I'm going to be presenting here in a couple minutes. I just wanted to say I'm really proud of you guys, and you did a great job presenting. I look forward to see what you guys do after you graduate here at Florida Tech. So great job.
Thank you.
Thank
Thank you for coaching us also.
thank
Yep.
you.
We have a minute or so if there are any other questions or, okay. If not, we'll take a break. I want to thank our speakers very much. That's
Thank
a
you.
rich round of applause, okay?
Thank you.